A very good morning to all of you. Now we are moving to the week 3 topics. Here we will discuss uninformed search techniques. Here we will see introduction to uninformed and informed search. In uninformed search, the first one is breadth first search. Every AI problems from Google Maps to games start with a search. So this slide shows how all AI search techniques are organized. We know that search means finding a path from start state to goal state. So searching algorithms that explores the problem space to find the path from initial state to goal state. Here we can see that G of state, operator and cost. State means where you are now, operator means what move you can take, and cost means effort or time or distance. So every search algorithm works on this same model. The search algorithms can be classified into two: uninformed search techniques and informed search techniques. Uninformed search techniques means there is no heuristics. Informed search techniques means users heuristics. We will see what is heuristics. First, we will see in this figure, the left hand side are uninformed search techniques and right hand side we can see informed search techniques. So uninformed search techniques is a blind search. That means no idea where the goal is. We can see that depth first search, breadth first search and cost first search are the examples of uninformed search. And we will discuss all these algorithms in detail. Depth first search means goes deep. That means search goes deep. And depth first search means that means goes level by level. And cost first search means lowest cost first. And the modified version of depth first search is depth limited search, and its modified version is iterative deepening DFS. Then coming to the right hand side, they are informed search techniques. So right side is smart search. It uses knowledge. So that means heuristics. Heuristics means we can say that how guess far the goal is. So the uninformed search techniques are best first search, A-star algorithm are informed search techniques. Here we can see that A-star algorithm that actually combines f of n is equal to h of n plus g of n. So that means h of n is the heuristics and g of n is the path cost. And this is actually the most important algorithm for real world AI. And we can also see bus first search that actually chooses best looking node. And then there are special problem solving techniques built on search. They are generate and test that will try until success, and hill climbing there is a step-by-step improvement. And then constraint satisfaction, we can see Sudoku and NQ are the examples of constraint satisfaction. Mean set analysis that reduce the difference to goal, and here the best algorithm is A-star algorithm. This slide shows the generic structure behind all search algorithms like PFS, DFS, UCS and A-star algorithm. So algorithm is same, only the friendlier data structure changes. So if you understand this slide, then you can able to understand all search algorithms. And here we can see a in description of general tree search algorithm and graph search algorithm. So here first we will see tree search. So here it is written it as a tree search function, and it will return a solution or a failure. So initialize the friendier using initial state of the problem. So friendier means it's a list of nodes waiting to be explored. So we start by putting the initial state into the friendier. So that is the root node. We are starting from the initial node that we can consider as the root node and no memory of the visited state. Then we have a loop do. If the friendier is empty, then return failure. So that means if there is no node left to explore, then no solution exists and it will return failure. Then choose a leaf node and remove it from the friendier. So choose a leaf node. Leaf node means node with no children yet. So if the node leaf node having no children yet means that can remove it from the friendier. Then actually in the case of the choose depends the choice actually the next node how we will choose. That is actually depending on the algorithm. For DFS, the deepest node will be selected, and for BFS, the shallowest node will be taken. If node contains a goal state, then return solution. So if our goal contains the goal state, then it will return as a solution. Then expand the choose node, adding the resulting node to the frontier. So that means here we are actually every search algorithm checks for the goal state or after removing from the frontier. So expand the choose node and apply all the operators, and we will choose the next node and we will add to the frontier. So here we can say that apply all actions, generate children and add them to the frontier. That is tree-search algorithm. Next is actually graph search algorithm. Here also it is written as the graph search algorithm. And we can say that here it will return a solution or a failure. Then initialize the frontier using the initial state of the problem. So here initialize the explode set to be empty. Then here we can see here we have a explode and frontier. The frontier means to be explored. Explode set means already explored. Explode set stores already visited states. So here then initialize the explode set to be empty. So that means initially the explode set is empty. Then we have a loop. If the frontier is empty, then return failure. So that means if there is no nodes existing to be explored, so return failure. Then choose a leaf node and remove it from the frontier. We already discussed in the tree search. If node contains a goal state, then return it as a solution. That also we discussed. Then add the node to the explode node. So that means when we are moving to the next node, then that node we can add to the explode set. So expand the chosen node, adding the resulting node to the frontier, if and only if not in the frontier or explode set. So that means if that is not in the frontier or if not in the explode set, that means not already explode, not already open, then we can add to the frontier. So that will prevent the infinite loops and also improves the efficiency. That is very essential for the real world problems. All real AI system uses graph search. Now we will discuss uninformed search techniques in detail. Suppose you lost your mobile phone at home. So you start search every room, every table, every drawer without any clue. So are you using intelligence or using searching blindly? So this is a best example for uninformed search. So uninformed search, we can say that blind or brute force search. So that means there are search techniques that do not use any extra knowledge about the problem. The algorithm does not know which state is better or worse. All states looks the same to it. For example, we can say that in a maze, it does not know which path is closer to the exit. So this algorithm tries everything possible until it finds the solution. It tries everything possible until it finds the solution. For example, trying all password one by one or searching a name in an unsorted list, we can consider it as an example. Then, so here we can see no heuristic or domain specific information is used. So that means we already discussed what are heuristics. That means we can say it as rule of thumb or intelligence. So uninformed search does not use heuristics. And it does not estimate distance, cost or goodness of a state. It relies only on initial state, goal state and all possible actions. For the next we will see breadth first search. That is an uninformed search technique. Suppose you are searching for a classroom in a new building. So you first check all rooms on the ground floor, then first floor, then second floor. So is this depth first search or this breadth first search? We can call it as breadth first search or we can call it as level wise search. Here, in the case of breadth first search, it's a simple strategy in which root node is expanded first then all the successors of the root node are expanded next, and then their successors, and so on. So that means breadth first search expands the root node first. Root node means the initial node, then all children, then their children, and so on. So we can say that BFS explores the search tree level by level, and it never skips any node at a level. So we can say that in this strategy, no viable solution are omitted, and therefore it is guaranteed that an optimal solution is found. So that means it will never skip any node at a level, means that is why no viable solution is missed, and hence the optimal solution is guaranteed. So what do you mean by optimal? The solution with the minimum number of steps. We can say that shortest path in a unweighted graph, or a minimum moves in a puzzle problem. And how we can ensure this level by level expansion? By using Q or FIFO, that is first not inserted, then first expanded. So the memory requirement are bigger problem in this execution time. So mm, than the execution time, that means BFS stores all the nodes at a level, and as the depth increases, number of nodes increases exponentially. So the memory requirement is the bigger problem for the breadth first search than is the execution time. So that means BFS may fail due to memory overflow, not time. And here we can see the example. Here we have a search. You can see our root node is A, and A has two nodes B and C. Now we are moving to B, then open C. So that level is complete. After completing that level only, it will move to the next level. So B has two children, D and E. First it will open D, then E, then move to another children of C, that is F and G, then move to F, then G. So it is a level by level search. Next we will see the algorithm of BFS. So here we can see that how BFS actually works internally using an algorithm. This is a standard BFS algorithm. Here it is written as a function BFS, that is breadth first search. And here we can see that it takes a problem as input, and it returns either a solution path or failure if goal not reachable. And the first line you can see, create a root node and set the state as initial state and path cost as equal to 0. So that is a starting point. BFS always start from the initial state. And in line 2 you can see, check whether the initial state itself is the goal state. If it is the goal state, then what will happen? If yes, then stop immediately. For example, if start city is the destination city, then we will stop it. Then the third line you can see frontier. Frontier means not weighted to be expanded. So here in the case of BFS, the FIFO queue ensures the level wise expansion. And line 4, we have to keep a track of already visited state. We already discussed explored means already visited states. So that prevents revisiting an infinite loops. And next we will see a loop. There BFS runs continuously until a solution is found or no nodes left. Next slide you can see, if a queue becomes empty, no nodes to explore. That means if further there is no node to explore, so that, and we didn't get the goal state, so it will return failure. And next we will see, next line, seventh line we will see, remove the friend node from the queue. So this is the shallowest node. In the case of BFS, the shallowest node will be selected and we have to remove it from the queue. BFS always expands the oldest node first. Then in the eighth line we will see, mark the node as visited. So we have to mark that node as visited. That means that we have to add to the explode state set. That will avoid expanding it again. Next we will see, find all actions from current node. So that means we have to generate all the child nodes. So for example, from a city, we have to find possible routes. And from a puzzle, we have to find all possible moves. Next line we can see, we can create a new child node. So child node, there is for a child node, state, parent, action and path cost will be there. And next here we will see if child, in the case of child, it is not explored or friendlier, then that means that we are considered as a child. So that means it is not in the explored, that is not explored earlier, and not in the, that means we have to explore it. So that we are considering it as a child. So it will actually avoid duplicates and also prevent repetitions and improve the efficiency. Then as soon as the goal is found, then it will return the solution path. So BFS guarantees the shortest path. BFS find the optimal path. Then next line we will see add the child to the end of the queue. So we have to maintain the FIFO order that will ensure the level by search, and BFS expand nodes level by level using the queue, that is FIFO. Then stores the visited nodes using explode set and guarantees the optimal solution. Then we will see the advantages and disadvantages of BFS. BFS explores the search space level by level. Therefore, the first time the goal is reached, it is we can say that it is the shortest path. That is the minimum number of steps. So this is true when all step cost are equal. That means all path cost, if you are considering equal, then it is the optimal solution. Then, for example, finding the shortest path in an unweighted graph, a minimum number of moves in a puzzle are examples. BFS always finds the shortest path if each action has equal path, the equal cost path. So that is the first advantage. And then, uh, so next is actually can always find a call state if one exists. We can say that BFS is called a complete search algorithm. So BFS will explore all nodes at a given depth before moving deeper. So each level completed only it will go to the next level. So if a goal exists in any finite depth, then BFS will definitely find it. That is another advantage. So there are two advantages. First one is optimal and second one is complete. Then we will see the disadvantages. BFS must store all generated nodes in memory before moving to the next level. So we require high storage requirement is the disadvantage. So as the depth increases, the number of nodes growing exponentially and the memory usage become very large. So for example, if you are considering, we have a branching factor B. So each node having B branches. And the depth is D. So there are D levels. D depth is nil. Then we can say that there are the memory requirement we can consider it as B to the power D. So the memory requirement we can consider as B raised to D is the B raised to D uh, is the memory requirement. So this makes the BFS impractical for large search space and memory becomes a bigger issue than time. Next we will see the time complexity of breadth first search. So if you are considering a search tree, same thing. In the last slide also we have discussed. Each node has B child nodes and their number of levels is equal to D. That is our depth is D. D is the branching factor, number of children per node, and D is the depth of the shallowest goal node. And here, in the case of first node, that is we can consider it as level 0, there is only one node. And level 1, we have B nodes. Level 2, we have B square nodes. And level 3, we have B to the power D node, B to the power 3 nodes. Similar to that, At level D, there will be b to the power d nodes. So the worst case scenario, the goal node is located at the depth D. So that is the last. Then it is the last node generated at that level. Then the BFS must generate all nodes from level 1 to level D. So we have D levels. Then if the goal state is at the last level, last node, then it has to generate all nodes from level 1 to level D. So we can consider the total number of nodes generated, we can consider it as B plus B square plus B to the power 3 plus etc. up to B to the power D. So therefore, the time complexity of BFS we can consider as big O of B to the power D when goal test is applied at node generation. So there is a special case, that means test applied at expansion. If the algorithm were to apply the goal test to nodes when selected for expansion rather than when generated. So that means if the algorithm applies the goal test only when nodes are selected for expansion instead of when they are generated, then all nodes at D are expanded. Their children at a depth D plus 1 are generated. So the explode then total nodes explode will become B to the power D plus 1. So that means uh, we are goal test we are applying only during the expansion, not when generated. So the whole layer of nodes up to depth D we are already expanded. Then before the goal was detected and the time complexity will become big O of B to the power D plus 1. Next we will see space complexity. So the time complexity of b to the power we already discussed because b to the power d, where b is the branching factor and d is the depth of the shallowest solution. And here we will see space complexity. So in breadth first search, every generated node remains in the memory. So nodes are stored either in frontier, that is before queue, or in the explode set. So frontier means to be explored and explored means already opened. Then at a depth D, the frontier contains all nodes at the deepest level. And number of nodes we can say that B to the power D. So the space complexity of BFS we can write it as big O of B to the power D, where B is the branching factor and D is the depth of the shallowest solution. And we know that BFS must remember all nodes at the current level while generating the next level. So this causes an exponential growth in the memory usage. For example, we can see if we consider B is equal to 3, that is our branching factor is equal to 3, and we have 5 levels. So our D is equal to 5. Then that means that we have 3 raised to 5. So 3 raised to 5, that is 243. So all the nodes must be stored in the memory. So in this case, there is 3 to the power 5, that is 243. So all these nodes must be stored in the memory. So number of nodes is actually 243. Then we will see with an example, traveling salesman problem. A salesman must travel every city exactly once and return to the starting city with a minimum travel cost. This is the traveling salesman problem. Here we can see these are the cities A, B, C, E, D, and the path cost it is mentioned in this figure. That means A to C the path cost is 1, C to E path cost is 2, C to D path cost is 3, like that. So we will see the state space. Each state represents a city. So also includes a set of cities already visited. Then initial state, there is a start state, that is A we are considering as the starting city. Then we have a successor function, travels from current city to any unvisited city connected by a road. And then goal state, that is the
trip visits each city only once, that start and ends at A. So that means visit each city exactly once and return back to the starting city A. And the path cost means total travel distance or time. So TSP, that is traveling salesman problem, is an optimization problem because we want the minimum cost. So why actually use BFS to solve this TPS? We can say that BFS explores all possible routes level by level. So every path with the same number of cities visited is explored together. So BFS ensures uh, no route is actually skipped and all possible permutations are examined. But BFS is not efficient because of the for the large TSP.
We will see traveling salesman problem, how we can solve it using BFS. BFS generates all possible tours. Choose the tour with a minimum total path cost. So here we can see that from A we can move to C, E and B. So next level, first level A, then next level we have B, C and E. Its path cost also mentioned. And after completing this level, it will move to the child nodes. Here we can see in the figure, we can see that there is from B, it can move to D, then E. So A already explored. So here it will move D and E. So here the path cost also mentioned, it is D and E. Then from C it can move from D and E. So it is mentioned from C to D and E and path cost also mentioned. And then from E it can move to C, D and B. There are three child nodes are there and its path cost is mentioned here. And then after completing this level, it will go to the next level, that is D. From D, you can see from D, it can move to C and E. From B only the parent node, so there is no need to consider. So child nodes are E and C. So from D, it is C and E. And then from E, it is A, then here A is the parent node and B is the parent node, and here we have to consider C and D. So it is considering C and D, and path cost also mentioned. And from D it has to move to B, and B is the B is the one node, and then next is actually E. C is the parent. So here we have two options, E and B. And then from E, you can see here there are two child nodes B and D. A and C are the parent nodes. Then you can see B, from B here it can move to D, and there actually A and E are the parent nodes. So only one path, that is D. Then from C, A is the parent node, E is the parent node, and only D is there. D is the child node. And from D, there is B and C, E is the parent node. So there are two options, B and C. So we will complete all these nodes in this level. Then only we move to the next. Then C, you can see A is the parent node, uh, D is the parent node. So only we have one child, that is E. Then from E actually A, B are the parent nodes. D is also the parent node. So only one child, that is C. Then from C actually you can see that A, B, E are the parent nodes. So next child node is only E. Sorry, D. Then for D, you can see that from D there is a child node is C, and E and B are the parent nodes. So we are exploring all the child nodes of each nodes in this level, and we are generating the next level. Again, we are moving to the next. And when we are exploring the child nodes, we will not consider the parent nodes. And after reaching the leaf node means there is no nodes further to explore. So then we will calculate the cost. You can see if we are considering the first path, 4 plus 5 plus 3 plus 2 plus 3 is the path cost. So we will be adding and we will get 70. Similar to that, we will consider the path cost for each path. And here we can see we are getting the shortest is 11. So, and there are 11. So two paths are possible. You can see this is one path. So here you can see that from A, C, D, E, B, A. So this is the one path which has shortest cost path, and another path is A, C, D, E, B, A. So that is the second one. We can choose either of this. Thank you.